Kangsan and Tommy in Whitaker. Learning comments. I'm Tommy.
I'm Kangsan.
And we're here to teach you guys about bistability and hysteresis.
So we'll start off with the definition of bistability. So in a dynamical system, bistability means the system has two stable equilibrium states. It doesn't matter how many it has in total, but we need two stable states.
So the way you can think about this is if you have two holes or buckets, and there's a ball precariously placed in between the two buckets. A slight perturbation from the right or the left can send the ball tumbling down into the bucket, where now the ball's in the bucket and it's pretty stable. It doesn't want to go out once you take it out.
So now we're going to go into more of an example of a bistable system and teach you guys how to differentiate a bistable system from a non-bistable system.
So the example that we're going to use is x prime is equal to 20 plus 100 s to the fourth over 3 to the fourth plus s to the fourth minus plus 10x.
So we can tell here that the function with the s is a Hills function, while the 10x represents more of a linear function.
So the way we're going to solve for the steady states is by setting x prime equal to 0 in graphing the Hill function versus the linear function and determining the points at which these functions intersect each other. So the Hill function is going to have a sigmoidal shape as such, whereas the linear function is going to be linear, like so. And one can see that there are 3 points of intersections, therefore we're going to have 3 steady states.
And by definition, that leads us to say that we have two stable steady states and one unstable one.
So if we were to graph the steady states as a function of time, one can see that this top steady state will be stable. This middle steady state will be unstable, and this bottom steady state will be stable.
But we can also look at this same model and we can modify the constant in front, the 20, to be a greater number.
What this does is shift the Hill function graph up, making there only be one intersection or one steady state of the system.
So by definition, this can't be bistable because we only have one steady state.
And if we look at the steady state of the system, potentially this steady state can be a stable or unstable steady system, just depending on the scenario.
And if we were to shift the graph, the constant to be negative, and we shift the Hills function to be below the 0 axis, that leads us to have a system that can potentially have two steady states.
So one can see that our Hill function intersects the linear function 2 times.
And that leads us to our stability analysis, where we can tell that if one steady state has to be stable, the other one by definition can't be, because it will stray away from the second steady state.
Right. The next thing we want to talk to you guys about is hysteresis.
So a very generic example of a bistable system that doesn't have hysteresis is a light switch. So a light switch doesn't remember when you turn it on or you turn it off. It does the same thing if you turn it on right now or if you turn it on 100 hours later. So we'll segue into the definition of hysteresis, which is a time-based dependence of a system's output on present and past inputs. This basically means that the system remembers whatever you input it, and that elicits a different response based on the previous input. So when we were to talk about an example of an actual system that shows hysteresis, would be an example of the Ebola outbreak in Western Africa of 2014. We saw that it took many deaths before people actually realized we were dealing with Ebola. And once the countries received H from WHO, we saw that the system remained on although we had very drastically reduced number of cases.
So using this example, one can see that the signal required to turn the system on we'll denote that as S1. So once this S1 signal is achieved, the signal will turn on, or the system will turn on. And in the case of the Ebola outbreak, once the number of cases had approached this S1 signal response, then the response would be the UN and WHO giving aid to the African countries.
And with the aid, the cases and deaths reduced drastically, as we can see along the green line, but the system was still on because we wanted to get to the S2, where we had no cases and no deaths at all to confirm that the Ebola outbreak was completely eradicated from Africa.
So the benefit of using the hysteresis system is that, again, the system remembers if it's on or off based on the previous inputs, as what we told in the definition. So in a biological sense, if the immune response actually exhibits hysteresis, and so do many cell signaling pathways also exhibit hysteresis. So it's an important concept in biology.
That was all for today.
This has been
Kangsan,
Tommy,
and
Whitaker.